Welcome to the last practical stream in structured programming. Today we'll talk about interesting things again.
As always.
As always.
So we move directly to the slides, please. Thanks a lot. And we have a look on the content for today. So as always, we start with some organizational matters. And then we have a Menti Quiz again. So
pre-prepared for that.
Yeah, the link is in the description of the YouTube video. And of course, we have a look on the current topics. So we have a look onto Structs. So we start with an introduction there. And then we go back to the last stream where I started an example with heap arrays. And now we implement the structs there. And then we have also a binary tree at the end of our stream, which fits into the Christmas topic of today.
Okay, then let's continue with organizational matters. The grading of A2, the assignment interviews have already started. They are until Wednesday. The results, we'll upload them every second day, but don't worry if you immediately see your result. At the end, when everything is complete, we'll announce that again, and then you can check. And if then something missing, then you can write something on Discord.
Assignment 3, so it was published last Thursday, and by now also the repositories are created, so you should be able to work on it. And just to remember, assignment 3 is compulsory, so you need to pass at least 50% of the public test cases in order to pass the course. So even if you have already 50 points in the course collected from assignment 1, assignment 2 and the homeworks and the coding sessions, you also have to do assignment 3 and need to fulfill this minimum requirement to pass the course.
Okay, coming to homework 3, we delayed it one more week because for some reasons. I think you can read that up on Discord. The kickoff will be now at the 21st. Yeah,
that's it. And then we
let's
come
to the Menti Quiz.
I hope you all are registered to the Menti Quiz, but I don't think that's all of you. So at the moment we have 80 people watching our stream, so maybe we wait for a few more seconds. And thanks for the compliment in the chat. And at least I think there should be more people out there, and I hope that everyone wants to join the Menti Quiz, because let me see whether we really have 80. Yeah, 80 people. Okay, but we can't wait forever, so
maybe we didn't do Menti Quiz for too long of a time.
So let's start with those 37 people, I think. So there will always be a code snippet and a question there. Okay, so we have this code here where we call malloc twice, and then we do the null check. So we really follow the guidelines that we set up, and in this case we return, and otherwise we do something in free. And now the question is that fine? Is there some compile error, some runtime error? Did we do something unnecessary, or have we missed something in our code?
Okay, so quite a few of you are wrong. There are some statements missing in this code snippet. Let's take a look. So we have two mallocs here, A and B, and then we check if A is null or B is null. But what happens now if A passes, so if that works, so we get memory for A, then B fails, we get null. And then in here, we have, okay, B is null, so we go in here and return. But we don't free A.
So we need to free A in this case.
Yes, so that's the problem here.
And also the other way around, basically.
Yeah, it could also be the case that A is null, and then B works for some reason again, and then we didn't free B. So if you do checks like this, don't forget to consider every case and if you need to free something.
Then we continue with the next question. So let's do it like this. And it's basically the same type now, but with a small modification here. We just have one malloc call here. We check again whether it's null, and now we do what you have told us that we should do. We should free it. Then our program can do something and we free it again. So is this now all fine, or maybe the question is now a bit tricky here?
Yes. Okay, so the 100% answer is that some statements are unnecessary in this case. I mean, it's not an error or something, and it's also not really wrong, but the free of the variable a here is just unnecessary because we know a is null, and then we call free on null here, which is not an error, but it's just unnecessary.
Okay, then we continue with the next question. Now it changed a bit the question. So we assume now that there is not enough memory available. And the question is what happens here? So is all fine, or compile time or runtime error? And we allocate.
So with the runtime error, we mean a segmentation fault.
So we execute the program and it crashes, for example. Then basically we allocate memory, we get some input. And of course, we do not forget to check whether the allocation was null, and then we continue somewhere.
Yes, so here most of you were right. That's nice to see. So maybe can you spot the problem this time?
Okay, this time I should explain it. The problem here is that we start with the malloc. That is completely fine, but then we immediately read the user input and store it into the allocated region. However, if it did not work, then we do the check afterwards. So if it didn't work, then A would be null, and we would write to a null pointer, which would cause the program to crash. So we would have to change the order that the get at is after the check. Okay. And last question, and now you have to read the question.
Okay, so again, it's what about this code? So as the first two questions.
Oh, so we opened. We're very sorry. Why did this not work?
We did. So okay, we have one malloc here. We check it for null. We then have a realloc. Check the realloc for null, and return. I don't know why this code is not in Menti.
Menti does not auto-refresh in this case, because we changed the question, but obviously if we present it, it doesn't adapt to it. Nevertheless, we hope that you...
I hope you all saw the question. We're sorry.
But then explain why something is missing now.
Okay, so we have some statements missing. This is because this is not the correct way of how you do a realloc. Because if this malloc is fine, then here down in the realloc, this fails. So we we can't allocate more memory. This returns null. We set A to null. This is null, and then return. But we didn't free the original memory. Realloc doesn't free the original memory if it fails. So down here, we would still need to free A. But now we have another problem because A is null. But we want to free this A up here. So we need a temporary variable which we check against null. Then free the original A. And then down here if everything works, we can assign A to the temporary variable.
Okay, that was the Menti quiz. It was just a recap about all the malloc stuff that we talked about the last 2 weeks, which you should be really familiar, in particular after assignment 2 now.
Yes.
But now we come to something new. So the next topic that we discuss are structs. You have seen them, I think, 2 weeks ago in the lecture, but so maybe let's repeat that.
Just a quick recap. So with structs, we can basically define more or less as an own data type, and in structs we can group multiple single data types into one. And structs are always user defined, so we can create quite complex structures with those, where we just group other structs or simple data types together.
So I would suggest that we just look at the short program and code a bit with structs that you see them again. So we can close the Menti now and maybe we create some main.c. And I will just, it's the wrong keyboard layout. So some basic thing, basic hello world. And now we want to implement the snowman. Today it's probably doesn't fit the weather if I look outside the window, but nevertheless, I want to do this. And now let's have a look on how to define a struct. So in general, we learned we need to write the struct keyword, then give it a name, and the style guide claims that it needs to be written this way. And then we can write the parts of which the struct consists. For example, we could say it has a size. So a snowman could be the size, the number of snowballs, for example. And then we could also say that the snowman has a head, for example. So it can be either true or false. So this would be the default way to create a struct. And then it consists of that integer and that character. And if we want to create a struct now in the main function, so I should say this is just the definition on how the struct looks. This is not an actual variable, so you cannot store anything there. This is also not a global variable. It's like the same as there is an integer, we now have there is a snowman, but we haven't created one.
It's kind of like if you declare a function, you just say this function exists and not that there's already some data where you can store stuff or something.
Then we create that struct, now an actual variable of that struct, and for this we have to write struct, then the name, snowman, and I don't know, my snowman. So with this, we would create a variable called my snowman of the struct, and this is a local variable as we would have here in integer a, for example. But I think this is it looks a bit complicated to write always struct and then this complicated name here. Okay, can we simplify this? Yes. We can simplify that. We can also use a type def. And with a type def, we write this before, then there is the definition of the struct, and then we give it another name, and now we give it the same name but without the underscores. And now we can write, of course, struct snowman, but with using the type def, we can write directly snowman. And now
so it's just like any other type now.
Yeah, so like an integer, for example, and it looks much better. Okay, so this is the way how to create a struct here. And now how can we initialize it? So to initialize a struct now, we need to access the variables or the members which are in the struct. And how can we do that? We can write our struct, so the variable, and then with a dot, we can access the actual members of the struct. And for example, we could set now the size to 3 snowballs and the his head attribute to 0, for example, so it does not have a head.
Maybe if there are any questions up until now, you can ask them with the chat. So then if anything is unclear about structs, please just ask.
It's a bit quiet in the chat at the moment. Okay, this works here, but if we have, I don't know, not just 2 attributes here, but I don't know, 10, this is a bit lengthy, and maybe we can do something better here. And there is another option to initialize a struct directly. So we can also, if we create now a second snowman, we can use an initializer list as you know it from arrays. And then we write the values that we want to assign to. For example, it has a size 4 and it has a head. So this would already work. However, if we have a long list here, maybe it's not clear to which attribute or to which member which variable belongs.
So whenever you see this, you basically have to look up the definition of the struct to know which is the first member, which is the second member.
Okay, yeah. And for that reason, we want to find a better solution. And we can write here actually the name of the member that we want to initialize this value to. And we need to write the dot, so it's like here, like accessing it, and then the name and equals, and we can also do it for the has head attribute. And with this style, it's clear that the size is 4 and the head is 1, and not the other way around.
Does it ever make sense to not use a type-def struct? I'm not sure if you ever need to use a not type-def struct, but it definitely, there is a reason why we also put the name here. So we have 2 names, and we'll come to that later.
Oh, right, that's in your example. When I use the struct in a function, do I have to pass it like that? Yeah. As every other variable.
And if you pass the snowman like that to a function, it also gets copied, the whole snowman.
So all member variables. So we basically have 2 different snowmans then. One living in the function, one living in the main, for example. Okay, so that's fine. So we have seen now basically 2 structs on the stack. But what happens on the heap? So maybe we create now a pointer. So this also works the same as with integers, for example. We call malloc. Have I included stdlib? Now it's included. So if I call malloc here, I need to write, of course, size of my variable now. So in this case, snowman.
So and the important thing about size of is that you most of the time want to write types here. So not variables, you want to write types here.
And we can also, I think it should work with hovering over it. So our snowman has a size of 8 bytes, even though it has only 4 or 5 bytes here. So there's some unused memory that is also contained in this struct, just because it behaves better for the compiler. Okay, then check for null, which we will not do here because it's not that interesting. And now, how can we initialize the struct in the heap now? So maybe try it the same way. My small pointer dot size equals 3, but it doesn't work. So yeah, okay, it's clear because we have to dereference it. And in this case, we need to write brackets there because the precedence of the operators is that way. It looks a bit strange. Is there something better that we can do?
Yes.
Yeah.
So I hope everyone understands why we need to dereference there.
Yeah. Do you want to explain it?
Yeah, so we have a point. So here we had just a snowman here, which we could just access the member variables with the dot. So we always really need the type to access them with the dot. And here we have just a pointer. And dot size on a pointer doesn't make sense. So therefore we need to dereference the pointer to really get the snowman and can then access the size attribute.
But then I will show you a better way of writing this. So we can do this with one operation. If we write the pointer and we write a minus and a greater, so an error, then we can directly access the attributes. So this operator here is the same as dereferencing and then accessing with the dot.
There's a question in the chat. What happens if the struct is greater than 8 bytes? Do we need extra steps?
No, we don't need any extra steps. I will just artificially make it larger. For example, we can also store a name in it.
So now we have 25 more bytes in the struct.
So it has
because this is not a pointer, the array is really in the struct.
So it's like 26, 30, if I count correctly. And now if we hover over the size, it would say, okay, the size is 32 now, some extra space again.
It just sometimes rounds up. So yeah, because of some technicalities. Wenn ich im Struct einen Int-Pointer hätte, müsste ich das malloc im Struct oder in der Main-Funktion anwenden. Also wenn du einen Pointer in einem Struct haben willst, auf anderen Memory, dann musst du den Pointer auch in der Main initialisieren. Also du kannst nicht in der Definition von der Struct irgendwas machen. Du musst in der Main dann einen Wert zuweisen und in dem Fall wäre es eben malloc aufrufen und den Pointer in den Pointer reinspeichern.
For example, something like that. Okay, so just remove it again. Okay, that should be fine. So what have we seen so far? We have seen the accessing with the dot, the initializer list, and when we have it on the heap, then we need the arrow instead. And now this might be a bit awkward again, that we need to write here for all attributes the initialization. So maybe we can also use initializer list here. So we try it. Just remove that part because I don't need this in the moment. Let's see whether we can write initializer list here. Equals dot size is, I don't know, 3 and has had is 0.
You forgot the equals.
Oh, thank you. That's maybe why it doesn't work. Okay, it doesn't work. Unfortunately. Oh, we have to dereference maybe. Also doesn't work. So no, you can't use an initializer list on already created variables. So this is not possible. You really have to declare it and initialize it in one step.
It also wouldn't work if it's already on the stack. So maybe change this to my snowman 2 without dereferencing them. So this also doesn't work. You can just use initializer lists when you newly create a variable, like up there.
Okay, so this doesn't really help us, but we have one solution here. We could say, okay, we create just a temporary snowman. So now it's declared in this line, so we can really initialize it. And then we say, okay, my snow pointer dereference is the temporary one. And now this works. And this is just copying the content of this struct into, or on this variable into this variable. And this works basically the same as for an integer. But the difference here is, of course, that not just one attribute, but all attributes are copied.
So does typecasting not work? I'm not sure what you mean, but the thing is that what we're doing here is different from what we're doing here. So this here is just an assignment. We are assigning a value to some variable. And if we write type my snowman, so we are creating a new variable and then writing an equals. This does something a little bit different because here we are actually directly creating a variable with that content, and initializer lists only work when you're creating a new variable. So there's just special syntax for when you're creating a new variable that don't work with assignments. But what does work is that we can assign structs to one another, and then it really copies every struct member.
Yeah.
So this works.
Then there is also the question, what if you want to change just one value? If you just want to change one value of the struct, then you just use the dot or the arrow notation, depending whether it's on a pointer or it's just a local variable. And one more question regarding strings. So if we would have a string of the type char name 25, what would happen then if we copy it? So if we would write this statement here?
This would work. So you have to think about the assignment. It's just copying memory. And here, if you're creating an array like that, there is really that much memory in the snowman struct. And when you create a snowman, there are really 24 characters, and these are copied when you assign. But for example, if you would do something like this, then suddenly the snowman struct doesn't really have 25 bytes in it anymore. It just has these 8 bytes which represent a pointer.
And what does get copied now?
So if we now assign one snowman to another, the name doesn't get copied, just the pointer. So both snowmen now point to the same string. And if we change the string, the name of both snowmans would change. No, and yeah.
Yeah. So this is really a bit hard to think about that. What really happens there? Maybe draw it and look on the pointers there, but it's a bit more complex.
Yeah, but I think if you understand the difference between having a pointer here and having the whole array in the struct, and you think about that it only copies the contents of the struct, it should be clear what happens.
Yeah. Okay, that was the short introduction to structs. And of course we should free the malloc at some point, but that's your homework. Okay, let's have a look what comes next. So the code is as always in the slides. Yeah, and we continue with the heap arrays from last time, and where we want to implement the struct. So basically we stopped there because there was not enough time, and we also didn't discuss structs that much, so we stopped there and now we continue. Just a short recap. So we had this time scheduler where we said we have a number of days, and for each day we have a number of sessions, and for each session we want to input the hours, the duration of the session. And maybe we switch to the... Yeah, okay, perfect. So it maybe looked like that. So this could be an input, but let's go immediately to the drawing. So we said the following: we have some days here, and when we have some days here, we have a pointer to the sessions, and for the first session we had 1, and for the second session we had 3 hours, and for the second day we had 3 sessions with 1, 2 and 1 hour again. And that's what we have already seen. And then there was a question arising. So that's what we have seen. We did not know how long the different lists are. So we didn't know that, for example, that this list has the length 3 and this list has the length 2, simply because we couldn't store it. And now we need the pointer to the list, and we need to store the length of the list, and we want to implement a struct there, and that's what we're gonna do now. So we also want to recap the code very briefly. So that's what we've done so far. We read in the number of days. We created an array such that we can store an integer pointer for each day. We also read in the number of sessions for each day. So we iterated over the days and read in the number of sessions. We allocated enough memory that we can store for each session the hours, the duration, and then we can store the duration for each session. And then the problem was that we have here the number of sessions locally for a day. But if we want to print now everything, it was not possible because we lose the information number of sessions. Okay, and now we want to change this to structs. And I think last time I already gave the definition for the struct. So we write it directly with typedef, a struct, and we call it day. And each day should now store two information because we should store the length and the pointer to the list. So we have an integer length and an integer pointer to the list for the day. Okay, and now let's have a look on this line of code here.
You forgot to name the typedef.
Thanks a lot. We want to call it day. So basically, if we go back to the drawing screen, maybe you can open the, yeah.
Oh, okay.
Thanks. Okay. Okay, now it seems that it works. So basically, we want to change this integer pointer part here, which we have here. We want to change this now to something like this, such that we have an array of days, and each day has an integer for the length and has an integer pointer that points then to the list, and with that we can iterate through the list. So that's the goal. And now we want to change this in the code as well. So we have here an array of days. So we lose one pointer star and we only need one pointer again because the array just consists of days. Number of days times the size of a day. Then we can still iterate over all days, read in the number of sessions. Then in the schedule, we need to access the ith day. So this is correct. With the brackets, we already dereference. For that reason, we need now the dot notation. And the list should be the memory that we allocate. And this is still an integer here. And in addition, we can also store the number of sessions now in each day. And we could just use the same notation as here with referring to the length, but I will use a different one. So we could also write with pointer arithmetics here, schedule plus I. This would be the pointer to the correct day. Then we dereference it. And once we dereferenced it, we can access it with the point. So this would be just number of sessions. And also another notation would be that we could write schedule plus I. We have a pointer and now we can use the arrow operator here with number of sessions.
But of course the preferable notation would be the last one.
Yeah. So let's get rid of this at least. Okay, and now we've stored in each day, so in the array of days, we stored every time the length and also the list. And now if we want to access the schedule here, we need the schedule evaluated at I, dot list evaluated at j. So this should work. And now finally with that information, we can also print everything. So we have maybe a day counter day counter less than number of days, plus plus, and then we can also have a session counter, and we want to iterate for each day now over the number of sessions, so the session counter should be less than day counter at schedule at day counter, so we have the specific day dot the length, so this is the number of sessions, and we increase the session counter now.
I think you forgot to increase the session counter.
Thank you. Very attentive. And now we can print something like, I don't know, %d, and then the schedule at the day counter dot list at the specific session. And with that we can print now everything. Maybe I write here a printf.
So you separate the days. Maybe also space after you print each schedule. Yeah.
Okay, and let's try it out. So clang 2D array.c. Okay, the number of days is, for example, 2 days. Number of session for the first day 2, and the duration 1 and 3. And then for the second day, with, for example, 3 sessions with 1, 2, and 1. And then we would see exactly this result because we can now iterate over the specific lengths. And this would also correspond to the example here where we have those 2 days with 1 and 3 and 1, 2, 1.
Okay, so there's a question, why is it better to use a 2D array for this instead of a linked list where each node is a day? So if you want to use a linked list or an array, it's just how you use it. In this example, we know the number of days at the beginning and it doesn't change. So we can just malloc an array with the correct size, and we don't need to touch it ever again because it has a correct size. So a linked list might be overkill, but if you want to add days later on when the program is already running, then a linked list maybe would be a good idea, because then you can just extend the list without always reallocating the whole array of days.
And moreover, if you want to insert something in the middle of the array or list, then this is far easier with a list than with an array.
Yeah. In an array, you would need to shift everything that comes afterwards by 1, so you can create space so you can insert that. With the linked list, you just need to change a few pointers.
Yeah, I think that was also both questions here.
Yeah.
Okay, let's see. I don't think I have. Yeah, the code is always on the slides, but I think I'm done with my enhancement. And now it's your turn with the binary tree.
So, because you already talked about linked lists, I wanted to do something like linked lists today. By default, linked lists were a bit boring, so I chose something different. And maybe I also didn't want to write code which you could use at the assignment. You can do that for yourself.
What about array of structs, such as with the elevators in the second assignment? We maybe want to avoid passing a huge number of singular variables, instead packed all in one struct. Yeah, so basically what I did in my example, so also used an array where I had structs.
Of course, this example would have also been possible without structs.
Yeah.
We could, for example, have created a second array, size of days, and then store, I know, for day 1 at index 1 in this array the length of the list. But this would get very confusing over time.
Particularly with more than 2 attributes there.
Okay, then what is a binary tree? So first, the theory, a tree consists of nodes like a graph, and each node in this tree has a value and pointers to its children. And the binary tree is a special tree which only has 2 children. Notice the top is called the root, but maybe I'll just draw it. This will get much easier.
Very right.
Okay. So you can imagine a tree like this. We have a node at the top. Just to get the terminology out there, this is the root node. So when I say the root node, I mean the first node at the very top. Then in the binary tree, every node has pointers for 2 children, which are also nodes. So these are the child nodes of the root. Maybe this can have a value up here. Maybe this has the value 1. Then these nodes have the value 2. I don't know. And then each of those nodes can again have children. Like this. Maybe we store the value 3 there. So I hope it's clear why this is similar to a linked list, but it's a bit more complex. So it won't be that difficult in the assignment. So basically what we are going to do is that every node here is a struct. So this is a struct, and this struct contains, I don't know, in this case maybe an integer data, and then also a pointer, so a node pointer for, if you want to call it left, and then also a node pointer for the right child. So instead of just having a next node in a linked list, I think they did linked list in the last lecture, right?
Linked lists were done, I think.
We now just have 2 children, or 2 next nodes each time.
So basically, if you just look on the leftmost path in this tree, this would be kind of a linked list.
Yeah, so this could be a linked list. So if you didn't have any right nodes, then this would be a linked list. And if you didn't have any left nodes, just right nodes, we would have this linked list here. But with this, we can traverse this tree in any way we want. Okay.
I think you should be clear.
So let's try to implement something like that. Yeah. Let's create binary tree.c. And yeah, we want to print something. We want to create something on the heap. I want to create those nodes on the heap. Let's talk about structs. Up until now, we always gave structs 2 names. So we had something like this. Like that. But basically I could do more than 2 children here, hence not only left, right, but an array of children. Yes, so if you want to just have any tree, you could have an array of children, and then you could maybe in some node have 2 children, in some node have 4 children, and if you want to take it even further, then it doesn't even have to be a tree. So one node could have a pointer to another node which is some levels above, and then you have cycles in the graph and everything. So you could really do anything with this, but let's just stick to this simple example. Yes, it wouldn't be a binary tree, and it also wouldn't be a tree if you have cycles. But yeah, let's not talk about this. So we have this type test struct. I want to store a name there. And so I will allocate this somewhere else. I don't want to store the name in the struct. And I want to have a node pointer for the left node and a node pointer for the right node. Like this. Let's try to compile it.
You probably can't compile it as we do not have a main function yet.
Yeah.
But let's see.
Okay, but we are already getting the errors I want. Unknown type name node. Okay. You can see this is the reason now why we have two names. When we are writing this type def here, at the moment we are writing node in this struct. The type def is not complete basically. So the compiler just knows, okay, we are doing a type def, we're doing it with this struct, but the compiler doesn't know what we want to name this struct yet. So node pointer here, the compiler has no idea what this is. Therefore, we have the second name up here, which we can refer to inside the struct definition. This works because when we're in this struct, the compiler already knows that this struct exists. So to have self-referential structs, so structs which have a pointer to themselves, they need a name up here. So you can refer to it in the struct.
I have now a stupid question, maybe, but what happens if we do not write the pointer star, so we just create the struct node in the struct?
I mean, if you think about it,
so I shouldn't do it.
Should it compile or shouldn't it compile? This is an interesting question, and you don't have to know that much of C to figure it out. If you just think about what happens here.
Is this now my job that I figure this out? Probably we have a struct which contains a struct, but this struct needs to contain again two structs, and both of those structs need to again contain two structs, and so on.
Exactly.
It looks a bit impossible.
So this can't work. A struct in C always, as in that infinite storage, always need to contain type info. Always needs to always needs to know its size. So, because the compiler, when it wants to create the struct, the compiler needs to know how much memory it needs to allocate. But if we have the same struct inside of this struct, we can't figure out the size because, okay, this is 8 bytes, then how much is this? How much bytes is this? Well, okay, it has 8 bytes, and then we have again this struct, and if we look up how much bytes this take, we are again in this struct. So this is an infinite loop. So it basically, it can't work.
So also the compiler says
something about it. But if you use a pointer, it's fine. Okay, we don't have a main, but if we use the pointer, it's fine. Because we know how big a pointer is. Okay, now create a main function. I wanted to create the root node on the stack now, and then every other node on the heap. So let's call this root node, and we'll use the initializer list.
So you learned this from the introduction, right?
Yeah. If we're using an initializer list, we also don't have to follow this order up here. Is there something in the style guide about this?
I don't know. I don't think so.
So we can just, say first left, then right, and then we can create some data. Oops, I did semicolons, but I meant to do something like that. What we want to create here is some sort of hierarchy in our course. So we want to have Alex and David, and then the tutors below. So like, I don't know, a company hierarchy. It's the best thing I managed to come up with. So
I actually have to look up whether we include the right people now.
Okay. Let's. So we can access the root node now with the data. We can access left. We can access right. And if we can access left, we can set this as own pointer. We could say malloc here and malloc size of something, but we want to write a function which reads this from the input. This is just very basic. We want a function which allocates the node on the heap. I call it read node. I don't know. I also malloc the string on the heap. Let's use f and s to read the name. Then create a new node like we saw it. Let's call it node. Create it on the heap with the correct size. Let's say this is a pointer now, so you need to use arrow. Data equals data. Left equals null. And right equals null. So we don't send left or right there.
Then we need an equal there.
Oh.
And maybe you can make the terminal a bit smaller that we see more of the program.
Oops, sorry. Okay, so now we can call node left equals read node, and we can set the right node to something. Yeah, I don't have a return. Yeah?
Yeah, compile again.
Oh, okay. I don't return the node pointer. Oops. You of course need to return the node pointer from this function, otherwise it won't work.
So basically this function up there initializes a node based on the user input.
Okay. Execute. I know David, Alex, everything's fine. So we basically have the root node up top, and now we have two child nodes. Let's create a few more. We can now go, for example, do something like root node left, which we previously had David. And now we need the pointer because the root node is not a pointer, the left is a pointer, so we need the arrow. And you can now read some value for the left node again. And we can do the same with the right node of the left child. So if we would go to the stream here, we now said okay, we said left, we read a node, we said right, we read a node, and now we said okay, maybe we can do something like this. And now down here we said left left and left right, so we said okay, this is the left node, left left, we read this, left node, left right, we read this. And now let's also do this for the right node. So let's go right and then left and then right and then left and read both. So right, oops.
So basically we have now exactly the tree created as you've drawn it here.
Yes.
Except for the values that are stored in there.
Yeah, and we can also try this out. We can, if you enter something, we can say, okay, we have Alex, we have David, we have me, we have Michi, we have Lena, maybe we have Taman.
Okay, so basically we filled now our tree. Is there also a way that we can have a look on it? Do you want to show that?
So printing the tree would be rather complex. Because I would need to calculate some spacing with the ASCII characters, so I can print it like I drew it. But maybe we can do something different. We could say, for example, that in every node we ask the user, do you want to go left or right? Or maybe even print the names of the left and the right node. And then say, if the user wants to go left, we print the same thing again for one level below on the left node. So maybe just in the drawing a bit, we want to have some prompt here. Do you want to go left or right? Then we say left. Then we have the same prompt here, left or right. We go right, and then it says we're at the end. So we just want some way to traverse our tree. Let's call this, I don't know, walk 3, because we want to walk down the tree, and we give a root node. First we need to check, okay, if the root node doesn't contain any children. So if root left equals null, we now always assume that we could do something like, if left is null but right is a pointer, then we just say you have to go right or something. But for simplicity, I'll just, if any of those are null, I'll say there are no more options, and then return. Okay. So if we pass a node with no children in this function, then we'll just return. Then let's print the options. So we have a first option. We want to actually print the data there. So this is the root node, maybe the left node, and we print the data of that one. So we know this is not null because here we have the check. And we can print the second option. Oops. And print the data of the right node. Now we want to give the user a choice. We ask which option the user wants. We store it in choice. So we need to pass the address here. And then OK. If the choice is 1, this was the left node, we want to go left. I leave that open what this means. Else, if the choice equals 2, we want to go right. Or maybe just say else. I don't want to handle invalid user input. So, do we need to write now all of this again in here because we want this for the child node? I think that would be suboptimal. And this is where recursion comes in. Up until now we often said, okay, don't do recursion, especially for input, because it often doesn't make that much sense to do it for input.
So basically we just used loops there as always.
But here it really makes sense, because let's look what can a loop do. In a loop we can say, okay, let's go, I don't know, over all children. So we loop over this.
I'm sorry.
We loop over this one, and then over this one. But now in the loop we would need another loop to iterate over these children. But now if we have another level down here we would need somehow another loop or something. So this would get a bit complex with loops. We would need just to a pointer and then work down. It's possible, but it's not that easy. The much more simple approach would be to say, okay, we pass this as a root node, we look at the left node, we look at the right node, and then if we want to go left, we pass the left node to this function again as the root node. And then we execute this function on this node, which thinks this is a root node, and then says, okay, we have this function, we have this function. Node, not function. We have this node, we have this node, and then it would execute this function down here again, and then see, oh, we don't have any children anymore. Let's just return, and then we return through all functions back up. Let's implement this. So here we want to call the same function again, but this time on the left node, because the first one was the left node. And here we want to go to the right.
Okay, so let's try it out.
Let's try it out.
Maybe make it in... So just fill the tree, maybe in this way. As I did it before.
I think it was like this.
Yeah.
I didn't call the function.
Oh, you did everything back to the start.
Oh, okay, wait. I put the new root node here on the stack. So actually, to get a pointer to the root node, we need to take the address.
So the walktree function expects that the pointer up there.
Yeah.
Okay, so
and root left is fine because left is already a pointer, but our root node is on the stack and therefore it's not a pointer. So we need to give it a pointer. So we really combined everything in this example. Okay, like this. And as we can see, I did something weird with the new lines.
But it doesn't matter in this case. It's okay.
Yeah, okay. So we can choose, do we want to go left or right, or in this case, do we want to go here? We print the data of the left node, which is Alex, or do we want to go here? We print the data of the right node, which is David. So let's say we want to go right. We choose 2. We went right. This is our new root node. We now say, do you want to go left to Lena, or do you want to go right to Tamin? Now we can, for example, say left. And now there are no more options because here there are no more child nodes. And we exit the program.
Yeah, very nice.
Okay, so I hope this was clear.
Are there any questions?
You can look at this later again, so it's also on the slides. I think it's just a good example of how linked lists and trees and such work, and how we could traverse those, and when recursion, when you should use recursion.
And as far as I know, the lecture will also do something about binary trees today. So maybe they will repeat this again and will also build up on it a bit.
So the code is here. Yeah,
what have we seen today? We started with introduction to structs, where we in particular saw the initializer list and how to access the member variables of a struct. Then we had the heap arrays and saw that we can store a pointer and next to its length that we have all the information that we need. And finally we had also the binary tree, which is recursion, which is like an enhancement of a linked list. Okay, and then we come to
the last part, as always.
But today, as there was a quiz, there is
we also can see who won the quiz.
Yeah, maybe go to the next slide. Let's see. But the last question was a bit tricky.
Okay, so Toast won this quiz. Congratulations.
Yeah, now I'm hungry.
So, let's continue with your questions.
Yes. I see the lecture complains that we also did very brief thing about recursion, but they will tell you more about it. Okay. Everything was clear now what we did. Actually, you're true. That was not a toast. It was a burger.
Yeah.
So the question is, was it called by Menti toast or was it user defined?
I think Menti chose the emoji,
you have to,
right?
You have to go to the next slide because otherwise they cannot write questions.
Oh, okay. Sorry.
I'm sorry.
Okay. Yeah. Let's start with the questions then. Even though it was a burger called toast. Kann man die Lösung, den Code zu Assignment 2 irgendwie bekommen?
Nein. Nein, das wird es nicht geben. Besonders weil es ja nicht eine Lösung zu Assignment 2 gibt, sondern ganz, ganz viele Möglichkeiten. Und die beste Lösung ist deine. Und wenn deine noch nicht perfekt ist, dann kannst du natürlich auch noch über Weihnachten weiterarbeiten.
Ich habe für 2 nichts abgegeben, also muss ich mich auch nicht für ein Assignment-Interview anmelden, oder? Nein, dann brauchst du kein Assignment-Interview machen.
Ja, genau.
Aber du kannst natürlich immer fragen am Discord, wenn irgendwas vielleicht bei Assignment 2 unklar ist.
For assignment 3, would you recommend when reading the user input with fkts to just allocate a huge amount of bytes and then free it after using the input? Or you just set it to 10 bytes and increase it? The second option is, of course, the preferable option because you don't know how long the user inputs are. So, so no matter how large the number is, it can be too small. And moreover, you should only use that much memory that is actually used. So,
yeah, but it doesn't have to be that strict with that much memory that you also use. 10, if you also always increase by 10 bytes and then in the last iteration you just use 2 of them, it's fine if you don't shrink it.
Yeah.
Or even if you use 20 or 30 bytes. It doesn't matter as long as you don't just use a huge amount of numbers and then never resize your array.
Yeah.
No, I won't go into detail here. Yeah.
Okay.
You can always ask your tutor for what you did wrong with the private test cases. So we can show you these private test cases now.
And we can also show them in the assignment interview. We usually do that there. So would creating trees with more than 2 directions be unintuitive in C because of structs? Maybe it would be better in C++ where nodes could be class objects. So in general, this doesn't matter too much because if you would have trees with, I don't know, up to n childs, or even you have no restriction, just use a dynamic array for the nodes. And of course, you can think about structs in a more object-oriented way as it is handled in C++. However, it's not needed, so it's still fine with C, of course.
Yeah. And I don't think it's any more or less unintuitive in C. Just that with class object, you could do it a bit nicer, but basically it would be very similar, I think.
Yeah. Okay, that was the last question.
I just like the language, maybe.
And maybe you didn't have too much choice there as well. Okay, I think that was it for today. Not too many questions. So I think it snows again. In about 20 minutes there will be the lecture, the last lecture for Introduction to Structured Programming. And we wish you happy holidays, Merry Christmas, and much fun with assignment 3 as well.
Yeah, and the next homework.
And the next homework.
Yeah.
So the next homework is about her bachelor thesis. So please do it. It's really interesting. Okay, then bye.
Bye.